Good morning. Let us start. This was the last slide yesterday. Before we continue, as usually, any questions, anybody? All is clear. Yeah, take a microphone.
If the interference are not predictable at all, and we will not be able to know if they are present or not, the only solution is to take them into account if we calculate the uncertainty.
I did not understand the first sentence. If the interference is not
predictable, like
predictable,
we don't know they are going to be present, the only solution is to take on.
If you have no idea at all about interference, then you have no way to take to take it into account in any way, because you don't know. So that during method development and validation, you have to find out at least something about interferences. And if during method development, you also find out what might be the actual extent, and you know how to correct, how to avoid, and you have confidence. You are confident that during actual usage with your actual samples, you will not have any significant interference. Then you don't really have to take it into account. Again, let me just take a brutally simple example. Hydrochloric acid, you are titrating hydrochloric acid with sodium hydroxide, trying to find out what the hydrochloric acid concentration is. In such a titration, nobody speaks about any interferences. Yeah. So it is very much about the information that you have. But during method development, during validation, you also have to test for interference. We will come to that later on in the validation part. So that, for example, again, if you do, let's say you do some elements in soil, again, let's be copper or nickel or zinc or whatever, then you should check what other elements might interfere. And if needed, you add those other elements at some higher quantity to see whether there is any interference. And you might find that, okay, yeah, no, nothing really interferes very much, yeah. But there are some elements which in this soil, they are not present to any big extent, so they don't interfere. But in some other soil, sometime in future, they might be at higher extent, so they might interfere. So that you may wish to take that into account as an potential uncertainty source, that, okay, if there are high concentrations of something, then this can cause interference and assign some uncertainty contribution. What I just said is very, very vague. Of course, you cannot really operate like that. It has to be much more concrete, much more specified. But this is the essence what it is. If during validation you discover that something potentially might interfere in everyday work, and that something you are not really going to determine in your everyday work, because if you will determine it, you might try to calculate or somehow subtract the interference. So if something might interfere and you're not going to determine it in your everyday work, you should take this possible interference. There is sadly no such nice, easy answer. As you see, I answered in a pretty long way. There's no such nice, easy solution to this whole thing. It is very often possible that your sample types or matrix types are very diverse, meaning they can be very different. You cannot take everything into account during validation, so that eventually during work you might encounter additional interferences that you were not taking into account. I'm not saying that taking interference into account as an uncertainty source is a good thing. Yeah, much better is if there's no interference. But if it's there in regular samples and you cannot be sure that you manage to avoid, then you have to do something about it, and taking it into account as an uncertainty source is essentially the least bad option. Let me put it. Any other questions here? Huh? What? Yeah. Could you pass the microphone?
For the second kind of effect, like ionization suppression in ESI LCMS, can we use the internal standard to compensate for that effect?
This is what people mostly do. As I mentioned also in the last lecture, in let's say trace analysis, or more generally in when you determine low levels of analytes in LCMS, also in ICP-MS, etc., most of the time it is very advisable to use the internal standard. And yes, it can address ionization suppression, but it depends what internal standard it is. For example, if it does not elute at the same MZ ratio, at the same retention time, then the co-eluters for the internal standard and your analyte might be different, resulting in different ionization suppression, meaning that the internal standard will not really fully very well account for it. In this sense, the best internal standard is the isotopically enriched or isotopically labeled internal standard, especially if it's not deuterium, but some other isotope like carbon-13, because those are essentially identical to your analyte, but mass spectrometer can distinguish. It's not sufficient if there's just one carbon-13. I would say usually people say that if it's 3 MZ units apart from the analyte, then it's safe. Then also the low resolution MS instruments can separate nicely. And that one would indeed elute at the same retention time. And you would be able to essentially, if you use internal standard in such a way that it's isotopically enriched, it's not deuterated, but carbon-13 completely co-elutes, then you might say that the ionization suppression problem essentially goes away. Don't need to take it into account any other way. Of course, even then, you still need to validate your method by spiking, for example. Now, as you see, in many cases here right now, I'm not giving you answers about how do you take anything into account or how do you express. That will come later. Otherwise, this first part would be immensely big. Yeah? The main idea of this first part is creating awareness so that you have a kind of a checklist. Okay, what are the things I should think about? Okay, now, what we did not discuss last time, this thing here. So selectivity-wise, different techniques are, let's say, can be very different by their ability to do highly selective kind of analysis. We will come to that also later, but perhaps you can say some examples of techniques that are really highly selective or really not really very, very selective. Any examples here? Take the microphone.
Ion selective electrode.
Yeah, and is it a highly selective device or not really very selective device?
Selective.
Oh, it's a highly selective thing. Any other opinions about ion selective electrodes?
I don't have a lot about like that technique, but maybe not that selective. I think because like some other ions with the same characteristics, electrodes, so it's not.
Sadly, I have to agree with Maitane. Ion selective electrodes, the very name of the technique is highly misleading. It's the only technique that has the word selective in its name, yet it's one of the least selective techniques, actually. There is one exception where ion selective electrode is extremely selective, just stunningly good by selectivity. Can anybody guess what it is? Fluoride comes second. Sorry? Exactly. So the potentiometric measurement of pH is just shockingly selective. If you think the main interferent when you measure pH in, let's say, okay, first of all, whenever you measure pH in neutral or acidic solution, you essentially have zero interference. The interference as a problem just goes away completely. And whenever it's basic or alkaline, strongly alkaline solutions, then the main interferent is sodium ion. Lithium also, but lithium is so rare in usual samples that we can at the moment neglect it. So the main interferent is sodium ion. And now almost all ion selective electrodes nowadays, almost all pH electrodes nowadays work without any problems until pH 12. So if you generate with sodium hydroxide pH 12, there's essentially no interference at all. What pH 12 means in terms of sodium ion concentration if it's sodium hydroxide? How much, what is the roughly, very approximately the sodium ion concentration in sodium hydroxide if the pH is 12? A very simple question. You should know this. Interesting. Okay, now let's dwell on this a bit. This is. So again, I take water and sodium hydroxide. I make sodium hydroxide solution in water. My pH is 12. What is approximately the sodium ion concentration that is needed for that? Exactly, 0.01 moles per liter. Because if it is sodium hydroxide, then 0.01 molar sodium hydroxide has roughly 0.01 moles per liter of sodium plus and OH minus, and 0.01, if you take negative logarithm, you get 2, and if you subtract from 14.2, you get exactly 12, which is the pH. Now, in pH 12, what roughly is the hydrogen ion concentration? This is even simpler question. 10 to the minus 12. So, analyte concentration, 10 to the minus 12 moles per liter. Interferent concentration, 10 to the minus 2 moles per liter. If we take the ratio, it's 10 to 10. 10 billion times. So, without any separation, there's no chromatography, no nothing here, without any separation, your analyte and your interferent are swimming around in the same solution. One is 10 billion times more abundant, yet there's no interference. This is just shocking how good it is, because if you think about it, the very good, really good selectivities of most other techniques come from separation. Usually chromatography or mass spectrometry that separates. But here there's no separation. H plus and sodium plus, they compete for the same membrane. Yeah, they are attacking the same membrane. And there's 1 billion times more attack from sodium plus than there is from hydrogen plus. And yet it shows a pH without any. Sadly, this success story is the only one. All others, fluoride is very well very well put. Fluoride is the next. It's pretty good, but everything else is quite bad. I will bring you later on an example how nitrate selective electrode works. And for example, typical nitrate selective electrode is just roughly 100 times, maybe 200 times more selective to nitrate than to chloride. So that if you have 200 times higher concentration of chloride in the sample, it can generate the same signal as nitrate. So we're not just saying that, okay, some interference. It's the same amount of signal from the interference. Okay, sorry, I got distracted, but in fact, it's not a distraction. Ion selective electrode is a very good example of a technique which is not selective. Again, except pH. pH is perfect, yeah, but except pH, all other ions, when you determine them with ion selective electrode, you have to think very carefully about it. Okay, now we have Carlo also. Sorry, Carlo, I didn't notice your concentration in due time, but your answer is correct. But now, okay, ion selective electrode, not so good. Any other examples, or maybe some very nicely selective technique? Okay, could you pass the microphone?
Yeah, I was thinking about those technique of hydride vapor generator that forms a hydride form, such as, for example, arsenic. So the technique hydride vapor generation is very selective to determining arsenic, as when to compare it with other spectroscopic methods such as flame, ICP, and even, ironically, ICP-MS. You cannot avoid the interference with arsenic in ICP-MS. You have to use high resolution. So vapor generation solves that problem.
Okay, yeah. So this is about atomic spectroscopy, essentially, a determination of elements. And you are right. Those hydride methods are pretty good. It's not only arsenic. There are also some other elements that can be used. And this is true that arsenic does have lots of problems, actually, in atomic spectrometry. Some of you took the atomic spectroscopy course last semester. I think you are well aware that whenever you go to really low concentrations, then suddenly all kinds of strange ions start to interfere, all those adducts of oxygen and then argon and different isotopic combination of things. So there's a lot of those isobaric, etc., interferences and also polyatomic interferences if we speak of ICP-MS, and ICP-OES also has quite some. So yes, hydride generation, pretty good. And also, of course, what you mentioned, what is very good is high resolution MS. So if we speak about ICP-MS with high resolution, then for most elements, it is possible to make it very highly selective. So let's perhaps move on, but let us just conclude that typically any technique that involves separation is better selective than anything that does not involve separation. Of course, let's say the separation technique number one is, of course, chromatography. Separation technique number two is mass spectrometry. If these two are combined, like LC-MS, yeah, and especially if that MS is then high resolution MS, then you get the very, very, very good. Likewise, perhaps one more example, UV spectrophotometry can be done in principle in two ways. You can do it just as UV visible spectrophotometry without any chromatography. Find some reagent, yeah, that's selective, yeah, like nitrate determination, certain reaction is carried out, color is formed, and now you measure the intensity of color. But all the other possible interference are still inside the solution, so the reagent has to be a good one. And such simple, let's say, spectrophotometric determination without any separation typically is not maybe so selective. But it's completely other story if it is liquid chromatography with UV visible spectrometric detector or photodiode array detector. Because then, first of all, you separate, only then you measure the absorbance. So that second option typically enables much better selection. So that yes, whenever trace analysis is carried out, most of the time people these days use some separation technique. So most of the time it is impossible to do it in such a way that all the interference are swimming in the same solution which you are actually measuring. Hydrogen ion determination or pH determination is an exception because let's think about it. If it's pH 12, it is trace analysis. You are measuring something which concentration is 10 to the minus 12 moles per liter. It nicely qualifies as trace analysis. Yet you don't need any separation, and you cannot do any separation in this case. All right, so selectivity, extremely important. If I manage to bring to your attention that it's extremely important thing to take care of, then these slides serve the purpose. Now here are next things which also are creating uncertainty in measuring the sample, the customer sample. Again, repeatability. This is one of the most common ones. Yeah, whenever you inject the sample 2 times, you get slightly different peak areas. So all kinds of random effects influence it. It's always present. It tends to be very procedure, very method specific. Some methods have excellent repeatability, some methods not so good. Yeah, but in many cases, what happens is that repeatability is important, yeah? But eventually not such big uncertainties also. Oftentimes some other sources of uncertainty actually are bigger. Then I have put here again this drift of instrument characteristic during the analytical run. You may say, hey, wait a minute, that was already, yeah, we already discussed it when we discussed calibration. And yes, we did. And this is why I'm putting it in brackets here. And the brackets mean that this uncertainty source is like a joint uncertainty source, both calibration and the measurement of your real samples. You can account for this uncertainty source in either of these two, but you should not double count, but you can assign it to either of these two things. You cannot say that it is just one or the other. It's both at time. Since we already discussed it, we don't need to. Then the next one is something that we already discussed. Actually, this is memory effects or sample carryover, and this is, of course, the reason for this kind of arrangement that I showed you last time. With this kind of arrangement, you can find out whether you actually have that problem. So here there's at least some good news, yeah, for the change. That if you discover that the blank does not have any signal from the analyte when injected after the most concentrated calibration solution, essentially it's fine. You don't have that problem. You don't really need to. But of course, many times, no, not so good, yeah. In some, let's say, in some ultra trace analysis, sometimes what people recommend is that after every calibrant and every sample, you put blank. Calibrant blank, calibrant blank, sample blank, sample blank, control chart sample blank, control chart sample blank, calibrant blank, real sample blank, 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 blank. So blank, 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 throughout the method. Not a bad idea, actually a very good idea, but costs money. Costs money because per run, you can run smaller number of customer samples, meaning you need more runs for serving your customers, which means more time, more labor from the people, more work. Increases cost, but can be very efficient actually. So these blanks, certainly not a bad idea. In some in some techniques also you can do it in such a way that the blank runs are shorter. This then can save time. Yeah, if your typical runs are longer, you can run blanks for shorter time, but it's very dependent on what the technique is. So here we cannot make big conclusions. Yeah, I did not mention, but I think it already is obvious. This means that the previous sample contributes to the signal of the next sample. This is really highly method specific. And first of all, it is the issue in the case of the trace analysis. So it's a usual middle range concentration. Trace analysis, it also is, as I said, method specific, and it also is analyte specific. So there are analytes that are specifically sticky, like mercury, which I already mentioned. And it cannot really be quantified in any easy way because the magnitude depends on what was the previous sample. So it's probably the best way to try to simply avoid it. So that I would say that this is here one uncertainty source which probably you will be able to avoid just using blanks, and then don't really need to figure out any kind of quantitative assessment. So, any questions here? Apparently not. Let me just for checking, please raise your hand who understands all those things that we've been discussing today. Okay, good. People on the internet. Hamdi, 2. Yeah, well, okay, good. Yeah. In any case, people on the internet, you always type your questions immediately when you don't understand. Yeah, don't wait for me. Yeah. And now, this is a kind of a summary slide. So, as I said, you have to think about all of these uncertainty sources. It does not necessarily mean that you have to quantify all of them. So again, for example, if you measure pH, this is a silly example, but still, if you measure pH, you don't need to think about extraction recovery, for example, because you don't extract it. So you have to think what really can possibly impact your case. And now, those that you either find or you have reason to believe that have significant influence, you have to try to quantify. Of course, again, whenever you can simply avoid them, much better. Yeah? If you cannot avoid, then you should. If you ask me, hey, yeah, but how do I know in every special case how important something is? I would say this will come with experience, first of all. Simply have to work in some field for a long time, then you start recognizing those. And of course, you hear from more senior people who have already been working for some time. And then, what I also said already, but let me just repeat, you do not need to quantify all of them individually. They can be quantified in batches. So that, for example, all those analyte losses, which can be because decomposition, volatilization, and not enough extraction, and then absorption, and so on, those usually are not separated. Those effects. They are all taken into account in one batch using, let's say, recovery determination, and then uncertainty of recovery tries to take into account all of those jointly. Yeah.
Need to decide to plan specific experiments if you want to target rate uncertainty.
Yeah. Yes and no. If you want to use the ISO-GAM modeling approach for uncertainty evaluation, then usually you need to do at least some special experiments for determining uncertainties. You may, okay, almost all of you, 2 of you were not there, but almost all of you were in the winter school. And you saw Irja Helm's presentation about dissolved oxygen, where she explained the uncertainty sources. And you saw different graphs and things that she showed. All of those were based on special experiments that she carried out for quantifying the uncertainty sources. So that if you use the model-based uncertainty evaluation, yes, most probably you need. If you use the validation approach or the Nordtest approach, as I'm oftentimes referring to, then you need to determine bias or need to determine recovery. This is something you have to do. Yeah? And then you need to maintain a control chart so that you will have the, let's say, within lab reproducibility. I'll explain all that later on in detail. Yeah? And if you do those things, then they enable you to take into account all uncertainty sources without you needing to take big additional experiments from any other thing. So that depending on how you address uncertainty evaluation, you need to do, or you may need to do different things. We will see later on how. It's a very good question. So that yes, at least some level of experimentation is always needed. And of course, you are never saved from method validation, which in itself is also a kind of set of experiments. So, and this is now the summary. I've already said. So the ability to recognize uncertainty sources and the ability to eliminate or minimize them. One of the most important things that you have to learn, yeah, for becoming an analytical. And I would like to say that these things are actually more important than knowing how to evaluate uncertainty. So if you are good in eliminating uncertainty sources or minimizing their effects, this is even more important. Uncertainty estimation is also important. Yeah, I'm not saying it's not important, but being able to minimize uncertainty is even more important. I think you probably all agree that instead of being very good at evaluating huge uncertainty ranges, you would rather be happy if you can make those uncertainty ranges narrower, even if you maybe are not as good at evaluating them. So your results will be more correct. And now, what about relative importance of the different uncertainty sources? I already mentioned some of that, but perhaps you want to ask something or comment or voice your opinions. In your opinion, on the basis of what I just explained, what might be the most important uncertainty sources in chemical analysis? Most of the time, again, we speak in very generic terms here. Can be in some cases, yes.
Sample prep.
Yeah, one of you said sampling, the other one of you said sample preparation. I would say that these two are really the two big ones. And if I want to put like some kind of the big three, yeah, I would put sampling, sample preparation, selectivity. Selectivity and interferences, yeah. Of course, as you remember, sampling uncertainty does not always enter your uncertainty budget. But in case it does, it often is very big. Yeah. Sampling, sample preparation, and interference. And contamination, by the way, jumps into sample preparation as a subset of, or a subcomponent of sample preparation most of the time. Good. If now no questions about this, we go to the second section of measurement uncertainty. Any Questions, comments, anybody? Apparently none. All right. So let's move to the next thing. Up to now, I have said almost nothing mathematical to you. So we were like completely avoided mathematics. We've only spoken about chemistry. Yeah? But now we go into mathematics part. Yeah. So first of all, some concepts. We can speak about the single measurement result, and single measurement result essentially means that you do your measurement once, but this, let me add here, includes, including all steps of measurement method, meaning if there is sample preparation involved, then this single measurement result is one result from starting from preparation of the sample and to the result. And if you then make another measurement, then you again start from sample preparation and you end with obtaining the result. And then, of course, oftentimes we do repetitions, and then we typically use the average value, what we present to the customer. Or don't have a customer, you have what you put into your thesis work, or you send to the production department, yeah, if it's an industry laboratory, etc. And the mean that you get is an estimate of the true mean. Let me repeat the question. What would be necessary to do if you would like to have the true mean? How could you, in principle, have the true mean? And that lots of means, exactly. Infinite, yeah. Infinite number of measurements gives you absolutely true mean. Yeah. You never can run infinite number of measurements, so you never achieve a true. Okay, but yeah, this is this. But now, suppose you still manage to do infinite number of measurements. In practice, I would say 100 is so close to infinity that is pretty much the same thing. Yeah, and 100 measurements can be done. So it's a lot of work. Almost nobody ever does that in that such a way, but still. But now this true mean is not the same thing as true value, and this actually we already explained. And my question to you is now, what is the difference between true mean and true value? What is the difference? Oh, explain. Yeah, take a microphone. Yeah.
One count the random and systematic effect, and the other one just the random. So this is cut.
And which is now the one? Which is the other?
The mean was taken into account both value. No, the opposite. True mean just the random effect, and the true value random.
Maitane, you want to say the right thing, but I would word it slightly differently. If we think about it, what is true value? We cannot really say true value takes into account. True value doesn't take anything into account. It's just truth. Yeah. So that I would rather say that true value is not influenced by neither systematic nor random effects. It's simply absolutely true with zero uncertainty. True me is not influenced by random effects. You have got rid of random effects because infinite number of measurements. Yeah, you get really the true mean. But true mean is influenced by systematic effects. And if your measurement has systematic effects, those will deviate your true mean from the true value. Was this understandable? Okay, yeah. I am stressing this. Very often people think, oh yeah, we can get as close as possible to the true value just by repeating measurements. This strategy usually is not very. So in chemical analysis, people usually don't do more replicates than maybe something like 3, 5. You would not really find in routine analysis people doing, for example, 20 replicate measurements and trying to get very close to true value because they understand, okay, yes, we can kill the random effects, but there are quite significant systematic effects in most of the work, and those will not be affected. Not much point to do so. See later on that in some cases making many repetitions over a long time can be very fruitful, but that is not what you do for your customer's sample, but that is what you do for investigating your method and quantifying uncertainty. So that's a separate thing. But with your customer's sample, you don't usually do so many repetitions. Maybe I would say 2, 3, 4. I would not say people do more replicates for routine samples when they know. Okay. Now, from mathematical statistical point, we can call our measurement results as random quantities. Terrible thing to say. Yeah, you put all your effort into measurement, and then the teacher comes to. This is a random quantity that you are presenting. But the word random quantity should not be taken as any kind of criticism, because random quantity might have very narrow distribution function. Might mean that it's actually a good one. Yeah? In any case, it's random quantity. And random quantities are distributed according to something called distribution functions. There are numerous, many distribution functions that mathematical people use, but in our case, in this course, we only limit ourselves to 4. I maybe mention here and there maybe something else very briefly, but typically it's only the normal distribution, the student distribution, rectangular, triangle. These are typically sufficient for measurement. And of course, we start with the normal distribution. You all know this distribution very well. I'm more than sure you've seen this graph, you've seen this formula, you've seen essentially all that you see in this figure. And perhaps let me start with asking why is normal distribution the most important distribution for us? Why is normal distribution the most important distribution function for us? Somewhat simplified way, we could do a simplified kind of course, the same course in very simplified way, and address only normal distribution, all others. But without the normal distribution, we really cannot. Am I done? Yeah, it's pretty well said. Only don't say that the distribution follows our result, but rather our results follow the distribution. Yeah, it is that way. So yes, there is something called central limit theorem, which you may have heard. And if I put it in a very simplified way, if some process, it's not even only the measurement, if some process is influenced by a number of factors, influence it in all kinds of random magnitudes and random directions, then if the number of factors approaches infinity, then the distribution function describing that process approaches the normal distribution. And when I say infinity, you might think, oh yeah, infinity, oh, so many. But in reality, if your measurement result is influenced only by 5 uncertainty sources of similar magnitude, and if you then do a simulation and build a distribution function, it's absolutely indistinguishable by sight, by looking at it from normal distribution. And even as few as 3 similarly sized uncertainty sources make the distribution function of your output quantity or of your result so close to the normal distribution. Usually you already can use all the math that relates to the normal distribution without any problem. So you by far don't need infinite number of uncertainty sources, not even 100, not even 10. What is important is that those, let's say, 3 uncertainty sources should be of similar importance or similar magnitude. If one is very big and the other 2 are small, then it's not necessarily normal. We will come to such situations later on. Okay. Now, let's see what we can learn from this graph. So first of all, normal distribution is characterized by the mean value and the standard deviation around the mean. This graph is built in such a way now that mean is here, minus 1s, minus 2s, minus 3s, plus 1s, plus 3s. And now you see here is written 68.3. Can anybody tell me what that 68.3 means here? 68.3%. What does this mean? The meaning. Would you take the microphone? Probability of what? By the word area, you mean what area? Bounded by the green lines. So by the area, you mean this area, yeah? Right? Okay, good, yes. So that if your measurement results are distributed according to the normal distribution, yeah, and you know what is the mean value, you know what is the standard deviation, when you now make one more measurement, then there is 68% probability that it will fall into this area. Correct. And if you make one more measurement, then yeah, there's quite some probability that it will not be here in this range, but then it is 95.5% probability that it will be in this area here. So that 95.5% probability that it will be between this value and between this value. Then 99.7% probability that will be between. All right. So yes, this is indeed what this is all about. And in many cases, we can assume that our results really follow normal distribution. And then of course, what we do in such a case, our measurement result then is here. And can anybody say then what then in the case if we use the uncertainty, let's say the uncertainty based on this normal distribution, what this curve then tells us, if our measurement result is here in the middle, we know that our measurement result is characterized by or follows the normal distribution. And if this S here is our standard uncertainty of our measurement, what do the probabilities tell us in that case? This is maybe too early to ask, but let's see if you can make sense. But what the coverage means, what do you mean by coverage? I would very much like to ask, what do you mean by the phrase, the highest probability of our result?
That normal I probably can predict where.
Okay, I got your point now. This is, as I said, my question is perhaps too premature, but still, let us dwell on it for a moment. So let us assume that this is not just standard deviation, but standard uncertainty. Standard uncertainty is UC. We will later on come to it. This is the standard uncertainty, and this is your result, which already may have repetitions in it. So that your result is Ym, your standard uncertainty is S. You are presenting this result to your customer, so please, here is your result. Ym is the result, and standard uncertainty S, so please, here you are. What then this standard uncertainty and this whole graph would tell to your customer? Customer takes the result. What should I now think about? Please pass the cubic to the back row.
I think when we change to the standard uncertainty, that means the probability of the true value is inside already.
I think you are meaning exactly the right thing, but please say it in a different way. Try to say it again.
In fact, it's a count both random. Have the bias.
Now you are going too detailed. Let's leave for the moment completely out all random and systematic effects. Let's just say that this is the result. It's distributed according to this normal distribution. This is the standard uncertainty. And what information does this give to your customer? The first sentence that you said was pretty good. If it's rephrased, then it will be very good.
One.
Okay, yeah, this is pretty well said, yes. In principle, the customer will look at those things, and if the customer knows what all these things mean, aha, okay. The true value of the measurand, the true value of the concentration, whatever was measured, is within Ym plus minus 1s with 68% probability, 68.3% probability, and with 31.7% probability it's outside of that range. Moreover, the true value is within plus minus 2s with 95.5% probability. This all is on the condition that this s is not just standard deviation, but standard uncertainty. I'll come to that, why I want to make such a clear distinction. So that this distribution function we can sort of look at in two ways. One way is that, okay, you make your measurement, and now you make many measurements, and now you predict where your next measurement will be. Yeah? And for that, indeed, you use the standard deviation. But if you present your result to your customer and you use combined standard uncertainty, and if you can demonstrate or you can declare that the measurement follows normal distribution function, then for the customer, the information is, aha, okay, where is the true value? Aha, true value is within this range with this probability. And if you remember, if you go now back to one of the very first lectures when I started with explaining the uncertainty, I said, yes, there's always some probability associated with measurement uncertainty. We don't really have 100% probability. And here is the reason, because I think you probably are well aware that even in these ranges here, the normal distribution function does not become zero. It almost touches, but never exactly touches the x-axis. It will always be slightly above zero. Yeah? This means that there's always some probability of the true value being somewhere here, but that probability is usually very, very, very small. Yeah? Okay, let me stop now. You may have questions. Might not have been the easiest thing to understand. Could you send the thing? Yeah.
My question is, if we take into account that this is the standard uncertainty, then is the systematic effects taken into account into the uncertainty, or it could be that the systematic effects make these values of the percentage be false?
Brilliant. So good question. I didn't want to explain this now because I thought that maybe I will bring in too many things. But exactly, this is exactly the main difference between standard deviation and standard uncertainty. Standard deviation only takes into account random effects. But standard uncertainty, if it is, or let me be even more clear, combined standard uncertainty, if it is correctly evaluated, always takes into account both random and systematic. And once that is correctly done, if you have reason, or if you have, how would I put it? If you have correctly estimated the combined standard uncertainty, and if you can demonstrate that your results really follow normal distribution, that I can tell you later on how that is done. If you can demonstrate that your results really follow normal distribution, then you do not need to worry about systematic or random effects anymore. And these percentages are valid, irrespective of whether there's more random or more systematic, etc. effect. All that is already taken into account if uncertainty is evaluated in a correct way. Did I manage to answer? Good. Any other questions here? Okay, if no more questions, please raise your hand who thinks that understood what I was trying to explain. Okay, Sarah, how about you? If you did not understand, please ask. Okay. This is sometimes still not very easy thing to understand. Yeah, so you are more than welcome next time again, bring up, hey, wait a minute, could we go back to this slide? Let us explain again all these things. So I'm happy to re-explain if needed, but do at home, do something. Okay. Now we move on. Standard deviation. The standard deviation is expressed via this formula, which I don't doubt you all know very well, which of course nowadays we don't really usually need to write this because all those Excel, etc., they all have built-in standard deviation formulas. So this kind of standard deviation is also called experimental standard deviation. And the word experimental standard deviation means that this is an estimate of the true standard deviation. Again, an estimate. And what should we do to get the true standard deviation? Infinite number of measurements. Yes, again, the same thing. Infinite number of measurements would give us true mean and true standard deviation. But our standard deviation can be slightly higher, slightly smaller than. And also, we can call it standard deviation of a single measurement. Standard deviation of a single measurement, which means that if you've done many measurements, you've found standard deviation, you found mean, then you can say that, aha, okay, the next measurement that I will now do exactly the same way will have a result which will be in this range with 68.3% probability and within this range with 95.5% probability. So this is what is meant by single measurement standard deviation. It tells us something about the single measurement, single analysis or single experiment. Now, you may also be interested. What is the standard deviation of the mean? Why is that important? Very often you present as a result of measurement a mean value of some replicate measurement. And then to characterize, let's say, the random effects of that mean value, you should calculate standard deviation of the mean. Now, if you think about it, if a single measurement is a single measurement result is a random quantity, then the mean also is a random quantity. What that means is, let's assume we do 3 replicates. 3 replicates, we get the mean. Now we do again 3 replicates, and another mean. Again 3 replicates, another mean. We have a number of means. Those means will also be different to some extent. Yeah, they also obey some distribution function. And those means also have standard deviation. Yeah, you can calculate. Now, standard deviation of the mean would be useful for characterizing the mean the same way as standard deviation of individual measurement would be useful for characterizing individual measurement. Now, there would be 2, like, let's say, in principle, there would be such an approach to calculate standard deviation of the mean that you make 5 replicates, calculate mean, then make again 5 replicates, calculate mean, then 5 replicates. do many times. Now you have a lot of means, and now you calculate standard deviation from all those. People usually don't do that. A lot of work. Have to do so much work. It turns out that there's a much simpler way. If you have made a number of those individual measurements, and if you have made n individual measurements, the number of measurements, and it turns out that standard deviation of the mean can very conveniently calculate it with this simple equation. You calculate the standard deviation of the individual measurement just the same way as it was done here, and now you simply divide it by the square root of how many measurements. So that, for example, if you make 4 replicates, the standard deviation of the mean will be 2 times smaller than the standard deviation of the individual measurement. Easy. So this is just a mathematical way of easily obtaining standard deviation of the mean. So that, as a matter of fact, almost always people do so that they make some number of replicates, calculate the mean, and they calculate standard deviation of the mean from the same set of replicate values. They don't start reproducing those sets of replicates. No need, because they can. Was this understandable? Huh? Yeah, please. Do you have a microphone? Okay. Yeah, I got it. Okay, good. Now, this is probably not so difficult thing to understand. And now we come to what standard uncertainty means. So up to now, we've been speaking about standard deviations, and then we've been speaking about measurement uncertainty in very general terms. But now we bring these concepts together in some sense. And standard uncertainty is uncertainty expressed as standard deviation. Sometimes also we can say that it is uncertainty expressed at standard deviation level. And in those cases, if the results are normally distributed, this also means that the standard uncertainty is uncertainty at roughly 68% coverage probability, which of course comes from here. Standard uncertainty of some quantity is denoted typically by U, and this Y is then what is the quantity, and it is equal to the respective standard deviation. This is, of course, a very tricky sentence here, because that standard deviation can come from random effects, meaning truly standard. It can come from systematic effects evaluated in some different way, and it can be a combination of both. And now, although I already said it, but let me now hear back from you. What is the difference between standard uncertainty and standard deviation? Yes.
So, while talking about standard deviation, so if you make like multiple measurements, we get the mean value, and standard deviation means if we do an extra measurement, our measurement probability of that measurement falling into that range is expressed by standard deviation. But for standard uncertainty, it gives us the probability that the result that we are expressing, or the mean value that we have obtained, is inside the area or inside this range. It can be expressed as like plus minus. So it gives us the range of where our true value,
Close.
True value can be.
Okay. Anybody else want to try? Yeah, Hans.
Standard deviation takes into account only the random. It does not take into account the mean. So if we have a mean of 100, we can say that the mean value of 100 is 100. But if we have a mean of 100 and 100, standard uncertainty takes random and systematic.
This is what I would say is perhaps the best way of answering this. With just one small addition, depending on situation, standard uncertainty can take into account either only random or only systematic or random and systematic. Because you can also express standard uncertainty as an uncertainty contribution due to repeatability. In that case, it only accounts for random. But you can express standard uncertainty as uncertainty of calibration. Then it accounts for systematic effects. Then it can be standard uncertainty of pipetting, like altogether, in which case it involves both random and systematic. So that standard uncertainty can be like a container, taking into account different effects which can be random or systematic depending on situation. But standard uncertainty, but standard deviation only always takes into account random effects. Please raise your hand who thinks that understood. Okay. I think Carlo also held hand up at one point. Yeah, okay. Good. Yeah. And then we have this coverage probability and confidence level. I think I already explained that also in some previous case. Confidence level only addresses those random effects. So that, okay, you made many measurements. Now you have your like a Gaussian curve or normal distribution curve defined. And now the next measurement will be within this range with 68% probability. Or you can also speak about like the true mean is within this range with this probability. But confidence level does not take into account any systematic effect. But coverage probability, again, depending on situation, has to take into account also systematic effects besides random. We will see later on that those standard uncertainty contributions can be very different. So some of them address only random effects, some of them address only systematic effects, some of them address effects which are like combination of random and systematic. Now we come to how are in principle uncertainties evaluated? How can they be evaluated? And we have the or estimated or evaluated. And we have two types, like in principle different types of uncertainty estimation or uncertainty evaluation possibility. One is type A. And type A uncertainty estimates are obtained from replicate measurements. So you just repeat measurements, and typically type A uncertainty is expressed as a standard deviation. Standard deviation is the most common way of expressing type A. Very, very understand. The typical example is uncertainty due to repeatability of doing something. And if you have type A uncertainty estimate, then it has something which we call degrees of freedom. And number of degrees of freedom depends on what was the number of measurements. And typically it is, or usually it is n-1. Not always, but usually it's n-1. We will later on perhaps address some situations when it's not n-1, but something. Most of the time it's n-1. Okay, I think it's fairly clear. And then we have type B uncertainty. Type B uncertainty estimates are obtained without any repetitions or without statistical techniques, they can be obtained by different other means. For example, concentration of standard solution. Suppose you buy the standard solution, you open the document, concentration this, uncertainty this. Then this is typical type B uncertainty estimation. You did not do any repeated measurements. You got it from the document. Yeah? And a very common source of type B estimates are all kinds of certificates, documents, etc. Like, for example, if you buy a certified reference material, which has lead, cadmium, nickel, cobalt, etc., all determined, concentrations here, uncertainties here, then those uncertainty estimates in the certificate of the CRM are typical type B uncertainty estimates. Also, a pretty important type of, or pretty important situation where type B uncertainty comes into play is educated guesses and expert opinions. We will see later on that in many cases, sadly, which is not really a good thing, but sadly, we have to rely on, like, let's say, long-term experience. Okay, this value probably is not outside these limits. Yeah? So this is a typical educated guess or expert opinion, but sometimes can be pretty useful. Type B estimates theoretically have an infinite number of degrees of freedom. But in real-life calculations, and we will see later on when we will need those calculations, in real-time life calculations, we cannot use infinity, so we need to use some numbers, and typically people use either 50 or 30. 50 or 30 essentially means that it is so like sort of corresponds to so many replicate measurements. The number of degrees of freedom is so big, sort of indistinguishable from infinity. It may seem to you strange, okay, well, 30 is not really infinity, it's very far from infinity. But in this kind of calculation, it is very close to infinity. Like I said already previously, this central limit theorem, you need only, actually, in practice, you need 3 uncertainty sources of comparable magnitude so that your result distribution function will be very close to normal distribution. So you don't need infinite number. Yeah, you actually can get by with very, very small number. Now, a very important thing is here, which I did not mention at all with type A uncertainty, because if it is type A uncertainty, this information usually comes automatically. But with type B uncertainty, if there is correct type B uncertainty estimate, it should give you the information on the distribution. And I'll come to examples in the coming slides, what that means. So just plus minus, like 20 plus minus 2, without any additional information, is a type B uncertainty. But it really cannot be called correctly presented uncertainty. I'll explain what to do in such cases. Because sadly, information about distribution function is very often incomplete. For example, in instrument manuals or instrument documents, you often can get something like, okay, precision, blah, 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 plus minus this, yeah, accuracy, blah, 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 plus minus that. But nobody tells you what the plus minus means. It's expanded uncertainty at K2 level, expanded uncertainty at K3 level, maybe some rectangular distribution. Nobody. Now, quite often, people interpret type A and type B uncertainty estimates as being the same thing as random and systematic. Is that so? What is the, so why can't, or what is the distinction, or what is the difference? It's correct. It's not so. We cannot say that type A uncertainty estimates, okay, put it like this. Let me put it like this. If I say two phrases, type A uncertainty estimates always refer to random uncertainty sources, or type B uncertainty estimates always refer to systematic uncertainty sources, then one of these is wrong. The other one is more or less right. Which is wrong? Which is right?
Random effect and by systematic.
And what about the other phrase? Is type B always referring to systematic effects only? Okay, let me try to answer that. You see, these types and the effect random systematic, they are really different things. Let's take the type B estimates first of all. Type B estimate is also type B estimate if somebody has done full uncertainty evaluation and now writes it down into some analysis certificate, and you are getting this certificate and you simply see the uncertainty. For you, it's type B estimate, but it can contain both random and systematic effects. In fact, it can also contain only random effects. For example, if instrument manual tells you, oh, the repeatability uncertainty of this instrument is this, then it's a random effect. But it is evaluated as type B uncertainty because they only give you the number. They don't give you anything about how many repetitions were made, etc. Yeah? So type B can evaluate randomly. Type B can evaluate also systematically. All kinds of uncertainties can be presented in documents. Now, type A most of the time indeed evaluates random effects. So obviously, if it's repeated measurements and mismatch between repeated measurement results, it is a random effect by definition. But even here, it's slightly more complex. Let me bring you one example. Suppose you are doing titration. You are determining your titrant concentration. Suppose now that your titrant concentration determination, the main uncertainty is some kind of random uncertainty. Let's say it's repeatability. Yeah? You determine it many times. Yeah, you get different values. Now you calculate standard uncertainty. Aha, okay. This is now my standard uncertainty of the titrant concentration. Yeah. It is, I have evaluated it with type A evaluation. But what happens now? For all your next titrations and the next days, if you keep that titrant, suppose you make it for a long time, that titrant uncertainty will act as a systematic effect. Even though here you evaluate as a random effect. But now if you use that titrant in your future titration, it will be a systematic effect because it's slightly off from what you think it is. So you think it's, yeah, it's 0.1 moles per liter, or 0.1000, this is what you think. In fact, it's 0.1002, yeah? Slightly off from 0.1. So all your titration results all the next days will be slightly off. So it will act as a systematic effect, even though it was evaluated as a random effect. Why I want to bring these things and why I'm spending time here, we will see later on the very terms random and systematic are not absolute. The same effect, depending on situation, can count as random or as systematic. And this titrant concentration thing is now a very good example. You see, you would say, hey, wait a minute, it's of course a random effect. Yeah, because every time I determine the titrant concentration, I get slightly different result. But now, as I finally have my titrant concentration, which will be slightly off from the true value, and in all the future days, that will act as a systematic. Which the terms random and systematic effects, oftentimes I interpret as something very simple and well understandable. But if you dig slightly deeper, not so simple. They're actually slightly more complex than you may think. And being able to understand which effect under which conditions work as random or as systematic, very important. Let me ask you, please raise your hand who thinks that understood what I just tried to explain. Okay, who did not raise hand, please ask. You're not obliged to raise hand when I ask. You always can, you don't need to raise your hand. Instead, you can ask, Ivo, I did not understand anything. Come on, please explain me once again. Yeah, I will do that. Yeah, Mike Dane. Microphone.
But for example, in the example that you mentioned, today I'm going to obtain with my titration a certain value of the concentration, and tomorrow another, because it's like, it depends on how I am working with and like how I'm working. But every time I obtain a different value, how can something that it is always random, every day random, could be systematic in a long period of time?
No, the way you right now explained is beautifully random. So indeed, if every day you determine titrant concentration again, okay, today I determine titrant concentration, yeah, and the next day, then it really between days will be a perfectly random effect. But if today with this one titrant, that you determine the concentration today, you are now determining the concentration of 10 different samples. Then within the day, within today, will be a systematic. Because all 10 will be slightly off.
But this has to be the same type.
Yeah.
Yeah.
Only
different samples.
But yeah, different samples, but the same titrant. But if you tomorrow re-standardize the titrant, and the day after do it again, every day first you do is you start by determining the concentration of the titrant. Then across all those many days, it will be completely random. Yeah, sometimes high, sometimes low. Yeah, so in the long term, it will be random. But within a day, it will still be systematic. And I'm so happy that you asked this. Why? Because if you look here, this will be one of the big topics, hopefully on the next lecture, how this random versus systematic depends on time frame. Things that can be systematic within a day can be random in the long term. It's extremely important thing, which extremely important consequences for evaluating uncertainty and organizing. You actually, in a way, you guessed this thing, it seems to me already. Yeah, we will come to that next.
Random. Now we are in the case random, systematically we are titrating with same solution, different samples.
And again, if we say random becomes systematic, we of course need to distinguish. It is a random effect that influences titrant concentration. But the titrant concentration itself then in a systematic way influences your customer sample results. Yeah, it can be tricky sometimes. Okay, we stop here. Yeah, next time we will continue here. Let me see how many things we still have. Yeah, we have a lot of things. Yeah. So next time we probably still will not do any calculations, but next time will be Tuesday. But next Wednesday, it may happen that maybe we will do the first calculations that we are going to do. Let's see how it goes. Yeah, next Tuesday I will still come to that. But for today, this is the last slide. Yeah, and we will continue from here. Thank you.